what are the key points? The key points for the parent function y equals sine of t. Okay, so we go 0, 0 is 1 point. Okay, I'm going to go out to, so those are not wrong, but I'm going to go out to 2 pi. Because I think this, if we could do this structure, it makes things so much easier. I'm going to go out to 2 pi. So I'm going to define my x-axis first. So 2 pi, then I cut it in half, then cut that in half, right? And then I cut this interval here in half, and that gives me 3 pi over 2, right? This is the shortest distance right here that I will ever use when I graph any of these, okay? And it is always, so when we do the sine and cosine, it's always going to be 1, 2, 3, 4 intervals. Does that make sense? So this shortest interval, no matter what my period is, will always be the period divided by 4. Does that make sense? Okay? And we'll talk about that a little bit more later on today, because we're going to change the period on some of these things. So these numbers might change, but this is going to be defined as whatever the period was divided by 4, and then I can use that as a counting tool to develop the rest of them if I want to do it that way. If you're not a fan of determining the endpoint and then cutting things in half, it's up to you. So once we have those, we got 0. So the sine function we said started at 0, 0. Where's it going to finish? 2 pi 0. Okay. What's another critical point that is, okay, so pi 0. So those are going to be my x-intercepts. Okay. Now, at pi over 2, where does my y value go? Positive 1. Okay. At 3 pi over 2, where's my y value go? Negative 1. All right, so those then are my the 5 parent function points. We are going to connect with a smooth curve. Do your best of that. Okay. And then we can replicate that as far as we need, right? If I need to go to 4 pi, cut and paste it, and the exact same relationship of points will exist between 2 pi and 4 pi. Does that make sense? Okay. Now, the reason we're going to do this, I said yesterday, I'm going to start putting transformations on this thing. Okay. If we can take that point there, that point there, that point there, that point there, and that point there, and you can move them up, you can move them down, you can move them left and right, you can reflect them, and you can stretch them. Then you can stretch, reflect, shift any trigonometric function we come across. Does that make sense? Okay. My hope is that what we gather here from the next couple of days when we transform trigonometric functions is that we've already learned all the algebra to do this. Okay. The only new thing is recognizing these 5 points and then applying everything that we learned in college algebra to those 5 points in regards to transformation. Okay. So remember, every point on this curve was a theta, comma, y value from the unit circle, right? So when I look at the cosine function, because that's our next function we want to graph, what do you think the structure of that's going to look like as ordered pairs? Theta, comma, so here y equals cosine of t or y equals cosine theta, how you want to write it. But it's going to be theta or t, comma, the x value from the unit circle. Okay? But on the curve, on the trigonometric curve, that x value that came from the unit circle is a y value. Does that make sense? That gets kind of confusing because it's an x value playing the role of a y value. But the cosine, just like the sine, because it comes from the unit circle, starts at 0 radians, And when I get all the way back around one revolution, I get back to 2 pi, right? Okay. So the period on the cosine function is the same as the period of the sine function. Because that's when we start repeating, right? Okay, that's when we repeat on the unit circle, so that's where we repeat on the curve. Start cutting things in half again. Pi over 2, 3 pi over 2. Okay. What are the largest, or what is the largest x value that we can use off the unit circle that will become one of these y values? What is the largest number we can get? 1, right? What's the smallest number we can get? -1. So again, my y-axis should be defined by 1 and -1. Have we done anything different than what we did with the sine function so far? No, they're identical. The structure of the graph is identical. Okay. Now, when we construct ordered pairs here, still going to construct the ordered pair that has a radian measurement, or theta, or t, however you want to view it, as 0. So with 0 radians, the cosine is 1, right? Okay. So I'm going to plot the point 0, 1. So that point right that point right there, 0, 1. Okay. Now, just to create kind of a pattern like we did with the sine function, I could go and take a little pi over 6 is going to be, 0.866, so find that, maybe about right there. I go pi over 4, and that's going to be 0.707, so maybe about right there. I go pi over 3, and that's going to be at 1/2, so maybe that goes about right there. And then pi over 2 goes to 0, so right there. So I can fill in these little points right here. Does that make sense? Okay. Not going to do that right now because I think that's a little bit more work than what's necessary. If I go all the way around, so start at 0 radians, go all the way around to 2 pi radians, what would be the x value on that terminal point that will become the y value up here? 2 pi radians will have a value of 1. Okay, so at 2 pi, we're back at the height of 1. Okay, very similar to the sine function. The sine function, where it started is where it ended, right? In regards to its y value. Okay, same thing here. All right. Now the other parts here, the other components are a little bit different. Okay, because the sine function halfway in between was the same y value, right? Because it was a 0. It's not going to happen here with the cosine, but there is some pattern here. There's some structure. At pi, what is the x value at pi on the unit circle? -1. So at pi, -1, I'll plot that point. Okay? So you start at 1, you finish at 1 in regards to the y values. Halfway in between, you're at -1. Does that make sense? Okay? Now, as we look at what we just done, we've really, those 3 points, section our x-axis into 2 parts. You guys agree with that? Okay. What happens halfway in between that green section? I have to hit 0. Okay. At pi over, and that's pi over 2, right? Isn't pi over 2 right here an x value of 0? So I'll plot the point pi over 2, 0. What happens halfway in between here? 0 again. 3 pi over 2 has a x value of 0. Okay? So we plot starting point at 1, finishing point at 1. Halfway in between, we're at -1. Then halfway in between those 2 points, we have an x-intercept. Halfway in between those 2 points, you have an x-intercept. And that's the quick way, using symmetry, to help us graph that curve. Okay. remember that curve. It should be smooth, okay? We don't, so the change from 1 to radical 3 over 2 to radical 2 over 2 to 1/2, that's a gradual change. It's not straight down, right? Okay? So we want a smooth curve, gradual change down to that x-intercept, and then those values repeat, kind of going in the opposite direction here. And they repeat again here, and then repeat again there. So it's got to be a smooth curve. Okay? We need to be able to do that. Okay? Everything that we do from here on out in this chapter, the first step is to graph either the sine or the cosine. So, if we look at these two graphs in comparison to one another, okay, if we just look between just the one period, 0 to 2 pi of the sine function and 0 to 2 pi of the cosine function, they look very similar, correct? Okay. Would you guys agree that if I took this green one and moved it to the right, see if I can do this, minus a, because we're moving to the right, so I'm going to be subtraction here. Create a slider. Let's make my slider go from 0 to pi over 2. Let's see if that works. Oh, pi over 2. Okay. So I get this thing to go to 0, so that's the cosine function, right? If I move it to the right, pi over 2 units, does it become the sine function? That makes sense? What is pi over 2 as a degree? 90. So right now there's some algebra here that we'll have to do, but you guys remember saying that cosine of x, okay, and sine of 90 minus x should be the same thing. If I go cosine of pi over 3, I get that value there. So then that should be the same thing as sine of 90, so pi over 2 minus pi over 3, 90 minus. Does that kind of make sense? We had the relationship that, now this is from geometry, but I think we talked about maybe I don't want to say the first day of this class, but early on that we said that, oh, that's a terrible color. The cosine of A is equal to the sine of 90 minus A, right? Okay, or the sine of A is equal to the cosine of 90 minus A. And that's because they're complement or co-function relationships, right? Now the algebra I said, that's a little bit different because here we're not doing 90 minus A, we're doing essentially A minus 90, right? Does that make sense? But because of our even odd properties, we can go through a little bit of algebra and see that these two things relate equivalently, okay? And we'll do that later on at some point. But what I'm trying to get at here is that these things they're intertwined. They're directly related. They're not. I don't want to say that they're completely different things. They're very similar to one another. Is that okay? What will happen? And you guys did this with functions in college algebra. If I gave you a function in college algebra that looked like this, let's say I put a point there. I say fit poly to A, B, C, D. If I gave you those ordered pairs and I told you that this was going to be a third degree polynomial, you could have, from college algebra, now we would have made the points a little bit nicer so that the formula was a little bit nicer, but you could have generated that. Does that make sense? Remember doing that? Okay. Well, same thing happens. Okay, and we can go, I'll give you something like this. I know you can't see this right now. I can give you that right there, okay? And I can ask you, okay, well, what would you identify this graph as, okay? I look at that right now and I say, oh, that could be negative cosine of x, but this needs to be stretched down a little bit, right? So I'm going to put a 2 out in front here. And that overlaps exactly, right? But when I go and I look at the algebra, there are two different equations. Okay? But those two different equations produce the exact same curve, right? All right? So the idea here is that there's actually, and because of the periodic behavior here, I could actually do this. I could say negative 2 cosine of x minus 2 pi. There's another one that is the exact same thing as that first one. Does that make sense? Okay. So there's actually an infinite number of ways. When I present you one curve and I ask you to write its equation, there's actually an infinite number of ways of doing that. Okay. Now some of these are better than others. Okay. If I'm looking for simplicity, that's the simplest one, right? Okay. But if I'm looking for it maybe in regards to, maybe I give you that one, I ask you, okay, rewrite that so that sine function is being used, well, then you have to use that one. Okay. So that gets a little bit confusing eventually, but it happens because of how closely related the sine and cosine functions are to one another. All right, so our goal eventually is to do, like I said, do transformations. Okay, so I'm going to list here these are exact transformations that we talked about in college algebra. All right, written for any generic function f of x. So in college algebra, f of x might have been x squared, might have been just x or 2x or 3x. It could have been the square root of x. It could have been the logarithm of x. It could be 2 to the x or e to the x. It could be any function that we've talked about so far. Okay, we're just now adding another type of function to that list. Okay, but everything that we've done with all other functions can be done and is done with trigonometric functions. Okay, so in this case, I'm going to say f of x is equal to sine right now. Okay, so what this would look like would be y equals sine of x, and then we'll add to it some constant. Okay, that is the parent function, much like x squared would have been a parent function. And if I add a constant to x squared, doesn't that move x squared up? Okay, so adding a constant to sine of x moves sine of x up. Okay, subtracting from sine of x will move it down. Okay, this one here, okay, so the idea, let's say the parent function was x squared. The way this one here, this function being written as f of x plus c, that is meaning we're taking x plus 3, or x plus c, whatever c could be, and we're doing that. Does that make sense? What did this do to x squared? Moved it left 3. Okay? So when I want to move the sine function left, it's going to look something like this. That plus c becomes part of the argument. Okay? Because we've used the terminology, I've used the phrasing that we are going to add c to x before we run it through our function, before we evaluate it through our function. And when we do that, it's moving it left and right. Much like when I had x squared and x plus 3 squared, I'm adding 3 to my x before I run it through the squaring function. Okay? And when that happens, you move things left and right. If it's plus, you move left. If it's minus, you move right. Okay? An x-axis reflection, if I had x squared and I multiply by a negative, it flips over the x-axis, right? So if I have sine of x and I multiply by a negative, it's going to reflect it over the x-axis. Okay? Y equals sine of negative x, like that, is going to reflect across the y-axis. Okay? And we can, if we wanted to, use our even-odd properties. If somebody gives me y equals sine of negative x, our even-odd properties tell us, no, that's the same thing as negative sine of x. Okay? So if we go back to this here. I go y equals sine of negative x. Gives me that graph right there, right? Okay, over here in the blue, I'm going to go y equals negative sine of x. Is it the same thing? Yeah, okay. So this one's defined. Let's see if I can show you. The green one is defined this way. The red one is defined that way. But we know because of the even-odd property that those two things are the same. Okay. Let's see here. You guys remember these transformations from college algebra? HSRV. We want to do vertical translation. It doesn't really matter the other three, but we want to do vertical translations last. It's a good reminder because of the potential of moving something vertically and then reflecting it can be an issue. So good point there. So I've got I got two examples here. One doing a vertical translation, the other one doing a reflection. Just get the habit of how we're going to do this. And then I've got a list of rules that you can abide by if you prefer. But when I teach this and when I do these examples, I'm not, because I don't know them. And this is what I think about mathematics. And every textbook that you read, a lot of textbooks, especially if you guys remember doing conic sections last year? And there's a bunch of rules and formulas per each conic section for where my foci go, where my major and minor axes go, where my asymptotes go, where my vertices go. It's a nightmare, okay? This is really the same kind of thing in regards to what authors do in textbooks. They give you rules and say, these are true facts about every single shifted or transformed sine or cosine function. And you can abide by these. You can memorize those, okay? But it's a pain in the butt because that's for the sine curve and this is for the cosine curve. And you can see there's a lot of things that are the same, but there's also some things, especially starting points, that are a little bit different. And I don't want to remember all those. That's nasty. I'll give them to you if you're a person that says, yeah, I can memorize that in a heartbeat and I have a problem with it, then have at it. But I'm not going to teach it. I'm not going to demonstrate it that way. Does that make sense? Okay. So hopefully these two examples at least get us to recognize how I'm going to demonstrate this to you, because I think over the last 12 to 13 years that I've taught this, this is what has been the most acceptable technique from students. Okay, they're more appreciative of this process. One, because it's less memorization, it's less time consuming, and it's more, I think, linear in regards to the thought that has to go into it. Okay, so whenever you see a transformed function, first thing you're going to do is identify the parent function. Parent function is cosine x, right? Okay, and this makes sense, hopefully, because it parallels to what we did in college algebra. I'm going to have a predefined set of points that I am comfortable with on every single parent function. Okay, so I know the cosine, the 5 points off the cosine function. We know it starts at a height of 1, finishes at 2 pi at a height of 1, right? Halfway in between, it's at its lowest value of negative 1. The x-intercepts are at pi over 2 and 3 pi over 2. We know those key parent function points. And that's what I said earlier, is that we're going to need to be able to do that, because that's the starting point for transforming any function. If I can move those 5 points correctly, and it really boils down, if you can move one of those points correctly, and then do the same pattern to the other 4, then you can create any transformed function. So what is that 2 going to do to every one of those points? Right. Okay. Now, some of you might be saying, well, that's not adding to the end. We always talk about add to the end of the function, right? Okay. But y equals cosine x plus 2, written that way, and this is just the author's preference. Okay. When I wrote this question down, they didn't want to use parentheses around x for whatever reason. A lot of your advanced textbooks college textbooks won't put parentheses around the argument for whatever reason. Okay, so they'll then put the 2 out in front, because if I write it this way, it can be confused of whether there should be parentheses there or if there should just be parentheses there, right? Okay, but if I put the 2 out in front right here, okay, then there's no confusion. All right? And think about what this says. It says the y value is 2 more than what the cosine's y values were. Okay? So if this cosine value was 1, okay, so that point 0, 1 is going to turn into what? 0, 3. Okay? Now, I have the luxury of being able to change colors and all that kind of stuff. You guys probably don't. You're probably using a pencil or a pen. What I like to do is I start with these, my just traditional points as my parent function, okay? And then when I transform them, that point, like, I'll turn into an x. And then this one, up 2, turns into an x, 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 and x. Does that make sense? So now I know that all of the x's go with the same curve. Because eventually what we're going to do is we'll move that up 2, and now we might move it left some amount. So then when I move it left, all the points will maybe become like triangles or open dots or something like that. Does that make sense? So you can distinguish, which points are which. Because if you're just using the same dots over and over, and we do 3 or 4 transformations, you're going to have a dartboard of dots that you don't know how they relate. Okay. If you got different colors, obviously that might be an option as well. But now all I'm going to do is connect those with a smooth curve, and now I have that period from 0 to 2 pi of 2 plus cosine x. If I wanted to, and we haven't done this yet, but if I wanted to graph things to the left, okay, there's symmetry. Okay, we know that the cosine function is a even function, so it should be symmetric with the y-axis, right? So that point right there is going to go right there. This one is going to go right there. That one right there. And this last one right there. And I can connect that. Smooth curve. And now we have, between negative 2 pi and 2 pi, we have cosine x plus 2. Is that all right? Okay, so if I want to go the next one, I'll look at negative cosine x. Again, do your parent. So I always leave it up to you a lot of times on, especially in homework, if we were to give you like a handout and you have to do these by hand. I will leave the y-axis unmarked so you can establish where you want 1 and negative 1 so you can establish your scale. On tests or quizzes, the way I do a test and quiz written by hand, what stinks about this is, and the same thing happened in college algebra, is WebAssign's options and their structure for giving questions like this stinks. They give you an equation and they give you 4 options to pick from. Well, if I don't have a clue what I'm doing, can I just type that equation into GeoGebra and then or Desmos and just match them and get the right answer? But I have absolutely no idea what I'm doing. So what I'll do is I'll give you handouts, and I will scale everything correctly so that when I grade them, because if Jimin uses a different scale than Amari, which uses a different one than Haley, then I've got essentially 35 different questions to grade. Does that make sense? Okay. So I will set the scales for you, and then I will take the test on a transparency, and then I'll just take my transparency and lay it on top of yours to see if they match. Does that make sense? But in notes and homework, whatever, things I'm not grading, you would establish the scale on the y-axis how you see fit. So I'm gonna put 1 right here. I'll put negative 1 right there. Cosine. So I want negative cosine of x. But cosine, I'm gonna start with cosine of x. I'm gonna start with the parent function again. So parent function, cosine, starts at 1, finishes at 1, right? Halfway in between, down to negative 1. And then we get those, right? Okay, now the next thing we're going to do is we're going to take those parent function ordered pairs and determine what happens when we multiply it by a negative. So this is saying that the y values that we're going to graph are, or the y value is, the opposite of what the y value for cosine was. So the y value for cosine here was 1. Opposite would be -1, right? What's the opposite of that y value? It's opposite of that y value. It's opposite of that y value. Opposite of that y value. And now we've got those 5 points transformed. We effectively did our transformation. That make sense? Okay. Individual transformations, guys, are not going to be things that really throw you for a loop. Okay. It's when I give you something like, well, just look at this. When I give you something like this. Okay. Now that right there can be replaced with any of the 6 sine, cosine, tangent, secant, cosecant, cotangents, or the 6 sine inverse, cosine inverse, tangent inverse, sine, or secant inverse, cosecant inverse, and cotangent inverse. There's actually 11 different trigonometric functions that go in that spot right there, right? So you use sine as kind of the general or generic one. Okay. If we go back to college algebra, they use F just for regular general function. Okay. So if you remember back to college algebra, we actually had this written down in college algebra at one time: y equals a times f of bx plus c plus d. And we ran through and thinking, well, that's a vertical stretch. This stuff here deals with, this b deals with a horizontal compression. That is a horizontal shift, and this is a vertical shift. We did that. Remember doing that, or at least seeing that kind of image? Okay. It is the exact same thing here. It's just now we are putting in the word sine. Okay. So this number here tells us our amplitude. If you remember amplitude, okay, if I'm looking at my sine function, the amplitude was that distance there from the axis of wave, or in this case, because the parent function, the x-axis, to a maximum or to a minimum. That distance was our amplitude. Ends up being the absolute value of that number right there. Okay, it's the vertical stretch. If we go back to college algebra concepts. Okay, this B, we didn't deal a whole lot with that B, and we had the discussion in college algebra that B, if B is greater than 1, it's a horizontal compression. But in college algebra, a horizontal compression, because of the polynomial functions we looked at, a horizontal compression graphically looked a lot like a vertical stretch. So it was difficult to decipher those. So we didn't talk about them. Okay? Now we are, because a horizontal compression with periodic functions is it looks like an accordion. Okay? When I push an accordion in, okay, it all squeezes down on itself, right? Okay? And it looks like a compression, or is a compression. Okay? That's when that B value is bigger than 1. If that B value is between 0 and 1, it's like when the accordion is pulled out. Okay, so it's going to expand it or horizontally stretch it. So we're going to start talking about that eventually. This plus C, that plus C tells me how far I'm moving it left and right. Okay, now there's a little bit of a caveat here because of how this is written. Really what we want to do is we want to write this as A times sine. We're going to put a bracket here. We'll pull the B out of this, and we'll have X plus. We'll pull the B out of this as well. So I'm going to say C divided by B. I'm just going to call it still C. And then D. Okay? So that's really what we're going to look at, because now we're adding to X and not adding to BX. Does that make sense? Okay? But that will tell me moving left and right. Okay? And then that plus D will be moving up and down. The questions that become difficult, guys, is when that number right there, when B is something different than 1, okay? Generally, all the other questions that we come across, people do not have any issues with, but when we change that B to a 2 or a 3 or a 1/2, something like that, people wig out, okay? I'll show you many examples of how to do that. It's very simple, but you guys just got to remember to do it. So I told you that these are some properties that you can deal with if you want to use. Okay, the only one that we're really going to use in great detail here, that I'm going to remind us of, is the 2 pi over b. Okay, if we go back to, and this is the relationship here, this is how this is developed. If I go back to the sine function or the cosine function, and I write y equals sine of 2, not 2, let's go b times x, okay? And I let x be 1. That is our parent function right there, okay? If we look at just the interval between 0 and 2 pi, just look at that blue region, okay? When I make this b value change, okay, is there existing, let me get this back to 1. When I make that b value change, is there existing more oscillations of that curve inside that blue region? That makes sense? Okay. So when that b value is 2, okay, now I want you guys to focus on the region between 0 and pi. Okay. Would you guys agree that that is now the period for the sine of 2x? Because it starts repeating after a distance of pi, right? Okay. And that contrast is that's different than sine of x. Sine of x takes it from 0 to 2 pi to repeat. But when I put that coefficient on that 2 right there, that's going to change things. It's going to squeeze the graph down. Hopefully you can see I use the accordion concept. Take the orange graph, put your hands on the end of it, and push your hands together. This orange one is going to end up morphing into the blue one, right? And that's called a horizontal compression. Horizontal compressions exist or are developed because the period changes. Okay? So we'll use that one. That will define the period for all sine and cosine transformations. This is just the shortest distance if we want to label our x-axis. Okay? Whatever your period was, divided by 4, and that's how you can chunk your x-axis so that you can find your critical points. I'm not ever going to use this, but if you ever want to know what the phase shift is, it's bx plus c equals 0. Phase shift with periodic functions is analogous to a horizontal shift. Okay? But I never do it that way. Okay? I don't explain it this way, but you can do it that way if you want to. Starting point is always the opposite of c over b comma d for the sine function. The reason I don't like this kind of stuff is because there's a different rule for the starting point of the cosine function. So I got to memorize 2 different things, and people transpose them. I'm not going to use it. I'm going to use my starting point for the sine function is always 0, 0, right? Okay. And once I find 0, 0, then I'm going to move it left and right, up and down, as is defined in that information there, and that allows me to circumvent having to memorize this. Okay. So what I'm trying to get at, it's there if you want it, but I'm not going to use it. I'm not going to teach it that way. Okay. This one, so this is what I prefer. You see the difference between these two here. That one, the B, is input into the parentheses right there, right, in the argument. You see how the B has been taken out here? Okay. This is the one, when we graph things, this is how we're going to want to rewrite things, to use our transformations from college algebra. Okay. And if I look at that, then it makes all these, it makes that a lot easier. The phase shift, the left to right movement, is now just the solution x plus c, which if c is 5, x plus 5 would say, okay, you move it left 5 units. This is a much easier structure than what this one is, but they're the same. Okay, so what I mean by that, let me write one out here real quick in GeoGebra. If I go y equals, let's go -2 sine of 2x plus pi. Okay, that graph right there. Okay, if I were to rewrite this as y equals -2 sine, I'm going to pull the 2 out of this. So when I say pull the 2 out, I'm factoring a 2 out. So if I factor a 2 out of 2x, what am I left with? X. If I factor a 2 out of pi, what am I left with? pi over 2. Are they the same thing? Does that make sense? But because of the way this one is written right here, this right here, because I'm adding pi over 2 to the x before I do anything else to it, is telling me that this is the sine curve is being shifted pi over 2 units to the left. Okay? You cannot see in this one here, in this purple one, you do not see a pi over 2 to the left, right? But it's obvious in this bottom one. Okay? So that's what we'll start with on Monday. Tomorrow I'm going to post, and it'll probably be posted later tonight. Now, I don't know, later tonight might be 8 o'clock, it might be midnight. It just depends on what time I get home. Okay? But I'm going to try to post it'll be open before you wake up tomorrow, an assignment that is going to be graded like a quiz, but it's going to be set up like a homework. Okay? I think some of us could benefit from bolstering that quiz test. I think it's 45% weighted category. Okay? It's going to be open tomorrow morning. It's going to close off tomorrow night. Okay? So tomorrow's an e-learning day, right? Okay? So it's going to take place of us being in class. It's not going to be something that's going to take you 7 hours to do. It'll be reasonable. Okay? Maybe 9 or 10. I'll keep it in the ballpark of, depending on how knowledgeable we are about the stuff, should be able to be done in less than a period. Have a wonderful weekend. Thank you. See ya.